Hello. Today I'm going to be explaining the Apollonian Gasket. And just get started. First, let's talk about the history. To understand the fractal, we're going to have to understand Apollonius's problem, which is where the name comes from. Apollonius's problem is basically you want to find a circle that's tangent to three others. You can see right here, you have three circles. Problem is to find tangent circle. There are many different circles you can find. You can find one that's tangent to all three of these on the outside. There's 6 total you can find. So, why is that important? Well, you'll see later. Remember that. Did Apollonius ever make the fractal? Well, you'd think so. He's got his name right there. He made it, right? Nope. Apollonius did not make the gasket. He just made the problem where it comes from. Well, who made it? A German mathematician by the name of Leibniz in 1706, way after Apollonius died. How did he make it? Well, let's get started with generating the fractal. So we're going to start with these 3 circles. They're all tangent to each other. And with those, we're going to do a problem up here. We're going to do it twice. One inside all of the circles and one outside all of the circles. And this is basically going to be our starting point, where you can see these curving triangles. Look for these all around. These are going to be really important. What we're going to do is we're going to make a circle that is tangent to each edge of those triangles, or each side. Sorry. So let's make that real quick. Yeah. And we're going to do this for every single triangle in the shape. So let's just do that real quick. It might take a little bit, but we should get a nice filled in gasket. There we go. I'm not gonna bother to really make these look nice because hold on. Because they're really too small to matter that much. Make sure they look tangent at least. There we go. This one, tangent to each side. It's a little tough on good notes, but we can do it. Look at that. And the last, nope, that was all. So, are we done? No. We're gonna keep doing this forever. Now you just saw 3 new triangles popped up. We're gonna do the exact same thing in each new triangle. Am I gonna draw all those out? No, it'd take forever. But you can use your imagination. Each one of these is going to be filled in with a new circle forever and ever and ever and ever and ever. And that's the key. This will go on forever. We won't stop at any point. We won't stop with a certain number of circles. It'll go on forever with infinite circles. And that's what makes it fractal. A fractal is a shape that repeats forever. And as you can see up here, you kind of see how it goes on, and there's little ones being made all over the place. It goes on forever, as best as we can show in an image. Just a little side note, these circles don't have to start in this orientation or in this size. They can be however big or small you want and however many of them you want. Up here, this guy who made this started with 4 of them. You can basically go however you want as long as you keep making circles that are tangent to all 3 sides. And so, what does the math look like? First off, let's see the sum of the circumferences. You can think of this like the length. If you think about it for a couple seconds, you'll see we have an infinite number of circles. My Apple pencil's dying, hold on. We have an infinite number of circles. And so, with an infinite number of circles, which all have their own circumference, you're gonna have an infinite circumference. So, if we let this shape play out forever, the circumference will be infinite, or the sum of circumferences. This will obviously not change. Now, the area, it's kind of the same way, but in the opposite direction. Now let's think of the area as these spaces that aren't filled in by circles, right? When we make a circle, let's say we're taking away from the total area of the circle. So these are like empty space. That makes sense? So as we add more and more and more circles, we're going to keep taking away from the total area. And again, if we do this forever, we'll have infinite circles. And even though each new circle is smaller than the last, and you're taking away a little bit and a little bit more area, if you continue that process forever, you will eventually reach 0 area. It sounds weird, it's a little hard to comprehend, but takeaway is there is no area. It's 0. Because there's infinite circles, which each take away from total area, you're gonna keep subtracting forever and eventually reach 0. Do something a little harder. The area of a new circle. So let's look at it right here. Well, area is pi r squared, so look at the radius. Radius of the first circle, the outer circle, is 1. The radius of these 2 inner circles is going to be 1/2. In our 4th circle, we're going to try to find the radius of this. So, start off, we need to look at the curvature. So that is this curve, and this curve. And we're looking for the curvature of this. So what is curvature? Well, it's the same as the reciprocal of the radius. So this circle's radius is 1. So its curvature would be 1/1, or 1. This one, its curvature is going to be 2. Except, if we look at, we're trying to find this circle's curvature, right? These two curves, compared to this one, let me use a different color so it's easier to see. These 2 curves, compared to the one we're trying to find, they're on the outside, they're moving away. That makes them positive. See, this one does not look like that. It's curving in. This makes it negative. This is a negative curve. If, say, the circle was on the outside, then it would be a positive curve. But the circle's right here. Oh, whoopsies. The circle is right here. and so it's a negative curve. So what does that mean? Our outer circle's curvature is going to be -1 because it's a negative curve compared to what we're trying to find. Now, we have our numbers, right? We're trying to find D. These are all the reciprocals. So 1 over 2, 1 over 2, -1, 2, and 2, the curvatures. Now, we're trying to find D. We're trying to find this curve. How do we find it? This is Descartes' equation. This is an equation to figure out the radius, or the curve. So let's fill in all our values. We have 2 plus 8. I'm just gonna start it, or I can, yeah, make it a little simpler. We have 1 plus 4 plus 4 plus d squared equals -1 plus 2 plus 2 plus x squared over 2. These are 4 because they're squared. This is positive now because it was squared. Now let's make it all multiply by 2 to get rid of this. So 2 plus 8 plus 8 plus 2x squared equals -1 plus 2 plus 2 plus x. Oh, sorry. Plus x. All that squared. Let's keep going. Simplify all this. 18 plus 2x squared equals 3 plus x squared. I'm running out of room, but let's just move over to here. We're gonna move this x over. Or no, we're gonna simplify this. So 18 plus 2x squared equals, FOIL this out, 9 plus 6x plus x squared. Let's divide by x squared on both sides. 18 plus x squared equals 9 plus 6x plus, yeah, that's it, sorry. Now, move everything over, minus 9 plus 6x, and we're gonna, that's too big, hold on, sorry. Just gonna get x squared minus 6x minus 9 equals 0. Move this over, and what that is x equals 3. That's the curve, or sorry, D. It would be, I put x in, sorry, but x is D. And 3 is the curve. So the curve is 3. Then the radius is going to be the reciprocal. So the radius, d 1 over 3. This is 1 over 3. And you can do that out, pi r squared, you can get the area. That's how you can find the new radius, thus the new area of any new circle you make. This equation holds strong if we were to go and make this circle, well, let's think about it. It's interacting on, just make it a little better. It's interacting with three curves. So this is A, B, C, looking for D. And we can do this equation all over again. We can do it here, we can do it here, 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 it'll keep going. And the answer will always be different. Well, most of the time be different. So there's no set scaling factor, but this equation is how you find the new size. Now, the Hausdorff dimension, it's this number, 1.305. You may be asking, Jack, how did you find that? How do we figure out the Hausdorff dimension? I don't know. I have no clue. It's witchcraft, crazy math that I have no idea what I'm reading. Just trust me. It's 1.305. It goes on forever. That's all I know. That's what the website said. Sorry. And that's it. Here are the sources I used. I used this one to figure out the Descartes formula. I used this Wikipedia, this is the official Wikipedia page, just a starting point, also taught me how to make it. And I used this to figure out the history. Thank you.